This video aims at how to connect a diode, PN junction diode in forward bias, reverse bias. What are the effects of forward biasing and reverse biasing? If you draw a voltage current characteristics, VI characteristics, how the graph looks like. Starting with forward biasing. A PN junction diode, the symbol is a triangle with a line. The triangle side represents P region and the line represents N region. The diode is forward biased if P region is connected to higher potential positive and N region is connected to lower potential, meaning P region is at a higher potential compared to the N region. When you do the experiment, we are supposed to measure the potential difference and current passing through the diode. For measuring potential difference, a voltmeter of suitable range is connected parallel to the diode. In actual experiment, when you connect, the polarity of the voltmeter to be taken care of with respect to the cell. Positive terminal of the voltmeter has to be connected to the terminal where the positive of the cell is connected to the diode, and negative terminal of the voltmeter has to be connected to the region where the negative of the cell is coming. Connection from the negative of the cell is coming. In between devices don't mind, but with respect to the cell, the negative of the voltmeter should be connected to the negative of the cell. Ammeter is connected in series. Here also the voltmeter, like polarity is important. Ammeter also the polarity is important. With respect to the cell, minus has to be to the negative of the cell and the positive has to be to the positive of the cell. So both the voltmeter and ammeter are sensitive to the sign of the potential difference. With respect to the cell, both has to be connected negative to the negative of the cell and positive to the positive of the cell. Otherwise, these devices don't show any reading during the experiment. If you do an PN junction experiment in the lab. Now in forward bias, we connect P region to positive terminal, N region to negative terminal for a cell. So in forward bias, since the positive polarity will repel the holes, negative repel the electrons, which are the majority carriers on both sides. P side holes are the majority carriers, N side free electrons are the majority carriers. They experience a repulsion from the negative and positive terminal of the cell so that they move towards the junction. So the width of the depletion region near the junction start decreasing because the holes start entering towards the center and the free electrons start entering towards the center because of the repulsion from the cell. So P side to positive potential, N side to negative potential. The actual width was this much before connecting the cell, before biasing, this much. But since the electrons and holes enter from both the sides, the width starts decreasing and becomes lower and lower. Now the potential barrier for a silicon made diode, 0.7 volt is the potential barrier. For a germanium diode, 0.2 volt is potential barrier. Here P side is negative and N side is positive for the potential barrier. When you connect positive to P and negative to N, the applied potential difference is opposing the potential barrier. That's why the width of the junction is decreasing. So the effective potential barrier starts decreasing. the applied voltage support the holes and electrons, which opposes the applied voltage opposes the potential barrier. So initially the potential barrier is number 1, high voltage. When you increase the applied voltage, for example, if this is 0.7 barrier, applied voltage is 0.1, the net will be 0.7 minus 0.1. If you apply 0.2, 0.7 minus 0.2, 0.5. When you apply 0.4, 0.7 minus 0.4 is 0.3. When you apply 0.7, 0.7 minus 0.7 will be 0. So like that, the potential barrier continuously decreases, and when the applied voltage exceeds the barrier, there won't be any potential barrier, the junction becomes conducting. Since the width and the depletion region decreases, the resistance offered by the PN junction, the depletion region, decreases. For an ideal diode, the resistance becomes 0 in forward bias, because the total potential barrier and depletion region all will disappear, and the applied voltage exceeds the barrier potential. Now, once it's forward biased, a current in the order of milliampere flows through the junction, which is due to the movement of majority charge carriers across the junction. Holes which are majority move towards n side. Electrons which are majority on the n side start moving towards the p side. This process is called minority carrier injection. Holes which are majority on n side, if free electrons are the majority on n side, holes are the minority. Those holes are injected into the n region. The minority carrier is injected into n region. Same way, free electrons are the minority on the p side. From n side, the battery will push the free electrons into p side. So the minority carriers on p side are injected into the p side. This is respectively called minority carrier injection from n to p and p to n. Now the junction start conducting beyond a specific voltage known as threshold voltage, which is again known as knee voltage or cut-in voltage. This is that particular voltage after which the current in the forward bias starts increasing significantly. Means the barrier potential is overcome because the external potential difference exceeds the barrier potential. These are the points regarding forward biasing. Now reverse biasing. The p side must be connected to the negative of the terminal. So p side is connected to the negative terminal, n side is connected to the positive terminal, or better, p side is connected to lower potential compared to the n side. P side is minus, n side is positive, so p side is connected to lower potential compared to the n side. So when you reverse the battery here, you have to reverse the voltmeter and ammeter terminals also, because voltmeter and ammeter are highly sensitive to the sign of the potential difference, negative to negative and positive to positive of both the devices. The diagram better, instead of reversing all the three, you can draw just by reversing the diode. If the diode is reversed, then the cell and voltmeter can just remain same. Here, ammeter, voltmeter, cell, all the three are reversed. Instead of that, just reversing the diode will do. Now in reverse biasing, the points will be clear if the forward biasing points are clear. P side is connected to lower potential compared to the n side. So last time the electrons, free electrons were pushed towards the junction, so width was decreasing. Now the positive terminal attract electrons away from the junction, the negative terminal attract holes away from the junction. The width start increasing more than the initial width. So the potential barrier will increase because the voltages add up now. So here the width was much less. Now the width will go increasing compared to the initial width. Now the potential barrier was this much, the first one, 1. Now when you apply the voltage, if you apply 0.1 with silicon 0.7, it will become 0.8. 0.2 plus 0.7, 0.9. The effective potential barrier start increasing. Now because the barrier width all increases, the resistance of the junction increases. For an ideal diode, the junction offers infinite resistance in reverse bias. But the majority charge carriers even don't conduct. There are minority charge carriers on p side and n side. Here there are few free electrons which are repelled by the negative. Here there will be few holes which are minority repelled by the positive. They can move across the junction, creating a very small current. The current is very small and it becomes constant even for a small potential difference because the minority charge carriers are very few in number, not like majority. Now in reverse bias also, if you increase the voltage beyond certain value, the covalent bonds of silicon atoms will break. That lead to larger number of free electrons and holes. When you apply a higher potential difference, the potential difference positive terminal start pulling the electron out from the control of the silicon atoms. When the potential difference is sufficient to break the covalent bonds, large number of free electrons come out for conduction, holes also formed. This leads to a sharp increase in reverse current. So this particular potential difference is known as breakdown voltage. So these are the basic properties regarding forward biasing and reverse biasing. If one side is clear, the other side is exactly opposite of that. Then there is a voltage current characteristics like VI graph. It's called VI characteristics, which shows these properties as a graph. This is the forward bias in first quadrant. The current along the y-axis in milliampere. In reverse bias, the current will be only very in the order of microampere, very small. So microampere in reverse bias. Forward bias 0.2, 0.4, 0.5 and all not conducting. It starts from 0.6 because electrons have thermal energy. But if you draw a straight line down to this, it will be almost reaching 0.7. That's the threshold voltage. So no current till this particular value and significantly rise after 0.7. That's the threshold voltage. In reverse bias, the current is very small, microampere, and becomes almost constant as discussed because the minority charge carriers are conducting and they are very, very few in number. So the current becomes saturated maximum. But if the voltage go beyond certain value, the breakdown of covalent bonds of silicon atoms lead to large number of free electrons, holes available for conduction that can lead to sharp rise in current. That potential difference is known as breakdown voltage. These are the VI characteristics and the properties in forward and reverse bias for PN junction. This graph to be drawn after connecting, you increase the voltage from 0.1, 0.2, 0.3 beyond 0.7 and note the milliammeter reading. Take a suitable scale and draw the graph. Same way in reverse bias also, increase the voltage and note the corresponding microammeter reading. The ammeter has to be micro. Then plot the corresponding graph. That's a practical set. Thank you for watching.